Today we'll continue our discussion of vector line integrals. If we have a vector field in the plane, let's say, f of xy equals a function times I plus a function times j, that's a vector field. We may be interested in this integral. For instance, this calculates the work along a path, and it's also used in calculating the energy. The change in energy is the work along a path. So if we want to evaluate this integral, we said before we could, for nice functions, for nice paths and functions, say f is continuous and dr dt is continuous, then f dot dr can be evaluated by taking the integral of f dot dr dt. You just divide this by dt and put dt and go between the limits of t. So that was how we could evaluate vector line integrals. But lots of integrals in the sciences actually are what are called conservative vector fields. And for those, there's a second technique to evaluate them that is often a lot easier because it's very similar to the fundamental theorem of calculus. Remember, in the fundamental theorem of calculus, if you wanted to evaluate an integral from a to b, you could just take an antiderivative, plug in the endpoint, plug in the initial point, take the difference. That made integration a whole lot easier than taking the limit of the sum, which is the definition of the definite integral. So we use that all the time. Similarly, in the sciences, when a force is conservative, a vector field is conservative, then it's much easier in general to plug in the endpoint and plug in the initial point to take the difference of a particular function called the potential that we're going to find here. So let's look at how we can tell if a vector field is conservative. Think of it as a force field or something, right? That each point x, y, here's the force of this vector. It has a certain direction and a certain strength. We have the following theorem first. We'll make this definition. A vector field is conservative if it's the gradient of some function, right? And then if you have a conservative vector field on some open connected plane region, then it will satisfy this. df2 dx, the derivative of the second component with respect to x, will be equal to the derivative of the first component with respect to y, df1 dy. So if you want to show a vector field is not conservative, you can show that this is an equal. Similarly, in three dimensions, if you have a vector field with three components, I, j, and k, and it's conservative on an open connected region, then its curl will be zero. If you can show the curl is not zero, then it's not conservative. Now, suppose you want to show it is conservative, so you can apply this nice theorem I said we had coming up. Well, on a simply connected open region, meaning no holes in the open connected region, if df2 dx equals df1 dy, then it's conservative. And in three dimensions, if it's simply connected open region, then the curl f equals 0 means f is conservative on that region. So here's the case. This region here is open and connected. I draw a dot along the boundary, means it doesn't include its boundary point, so it's open. And then there's a path from every point to every other point, so it's connected. On this region, if the force is conservative, if the vector field is conservative, then df2 dx will be equal to df1 dy. Now this is an open connected region also. It doesn't include its boundary, but it has a hole in the middle. So this one is also simply connected, this one's not. The official definition is that every loop in here, every path that's a loop, can be drawn continuously to a point. And you can do that here, but here you can't. If you make a loop that encloses this hole, you can't shrink it down to a point continuously without exiting the region. So on this type of region, f is conservative if and only if df2 dx equals df1 dy. On this region, if it's conservative, then df2 dx equals df1 dy, but df2 dx equals df1 dy doesn't necessarily imply it's conservative. Now in three dimensions, it's actually a little trickier, the idea of simply connected. In three dimensions, if you have maybe a big ball of some sort, this is open and simply connected. You can actually take a hole out of the middle, and it's still simply connected because every loop in that region can be drawn continuously to a point. However, if you drill a hole clear through, right, from one side to the other, now it's not simply connected because you can put a loop around this hole and you can't draw continuously to a point and remain in the region. So it's a little different definition in the plane than in 3 dimensions. The idea, though, is that if every loop can be drawn continuously to a point, then it's simply connected. And in the plane, that means there's no holes in it, not even a single point. All right, so that's the ticky-tack mathematics there. Now let's see what we can do with this. The theorem, maybe we think this one is not conservative, so we just have to use that first theorem we wrote up here. We can't use our theorem that's coming up for conservative fields. If I want to show it's not conservative, I can check. Is df2 dx equal to df1 dy or not? df2 dx is equal to partial of y with respect to x is 0. Partial of f1 with respect to x, though, derivative of xy is y, partial derivative. Derivative of xy with respect to y is x. And these two are not equal. Consequently, this cannot be a conservative vector field. So I'll just have to apply the theorem we already had up there. Now, show that this vector valued function, this vector field in 3 dimensions is conservative on R3, the whole 3-dimensional space. Well, there's no hole clear through 3-dimensional space, so this is an open, simply connected region. I take the curl, and if the curl is 0, it's conservative, and if the curl isn't 0, it's not conservative. So on simply connected regions, this is a real easy theorem, it's just if and only if. So we take the curl, all right, ijk, the partial derivatives of the gradient, and the components of f down here, right? And I multiplies dz dy, which is 0, minus, minus d2y dz, which is 0. And then minus j times d dx of minus z is 0, minus d dz of x is 0, so 0j. And then k multiplies d dx of 2y minus d dy of x is also 0. We get the 0 vector. It follows that this is a conservative vector field. There is some function f that is the gradient of on all of 3 space. A lot of the problems we'll see in the book relate to this kind of thing. Given a vector field that we were either told is conservative or we've checked with this test to show it's conservative, what is the potential for it? What's going to happen is that theorem is going to allow us to evaluate the function if it's conservative. So we need the potential to use the theorem. If this is really conservative, then this is df dx for some little f, and this is df dy for some little f. So it says df dx is this one x minus y, and df dy is this one x plus 2y, minus x plus 2y. And so if this is the partial integral of f with respect to x, then f must be, if this is the partial derivative with respect to x, then f must be the partial integral with respect to x of this. Similarly, if this is the partial derivative with respect to y, then its partial integral will give the function back. So we do partial integral of this one with respect to x and partial integral of this one with respect to y to recover little f. And this one gets x squared, right? Integrate x, you get x squared over 2, but it's a partial integral. So integral of minus y is minus xy. Y is treated as a constant. Here this is a partial integral treating x as a constant. So integral of minus x is minus xy, but integral to y is y squared. Y is the variable, x is treated as a constant. And then in a partial integration, the constant can be a function of the other variable, an arbitrary function, right? Because the derivative of any function of y is 0 with respect to x. The partial integral with respect to x, the arbitrary constant, is an arbitrary function of y. Similarly here, x is treated as a constant, so the arbitrary constant here is an arbitrary function of x. What we've deduced by integrating the first component with respect to x and the second component with respect to y partial integrals is that these two have to be equal. For these two to be equal, you compare them. That term's the same. This has a y squared that can be part of h of y. This has an x squared over 2 that can be part of k of x. The only function that satisfies both of these is x squared over 2 minus xy plus y squared. Plus we can put an arbitrary constant that doesn't depend on either x or y. This is a potential for this vector field. We don't have to check this first. If we find the potential, we already know it's conservative. This is just a check ahead of time to see if we're going to be able to find this function. Most vector valued functions you can't find a potential for. They're not conservative. But this one is, we found its potential. Here it is. And just for simplicity, most people choose C equals 0. That's the easiest thing to do. And what you also see is that all potentials for this conservative vector field are equal to within a plus C. That's true in general. Whenever you have a conservative field, all the potentials are equal to within a plus C. It's like the fundamental theorem of calculus. All right. Here's the big theorem we've been working up to. If you're lucky enough to have a conservative vector field, F, a vector field is the gradient of some function, and that's a conservative a continuous vector field on an open connected region D, containing a curve C, then along any piecewise smooth curve C from one point to another in that region, the line integral is equal to the potential at the final point minus the potential at the beginning point. And that's it. It's independent of path. It doesn't matter if you took this path C1 from point 1 to point 2, or this path C2 from point 1 to point 2, or this path, whatever path you take, the line integral has the same value. It's just the potential at the end point minus the potential at the beginning point. It reminds you of the fundamental theorem of calculus, right? We're going to make that analogy at the end again. So all three of these line integrals are equal, and they're equal to the potential at the end minus the potential at the beginning. Consequently, there's a very interesting result. If you take a line integral around any closed path, you go around and come back to the point you started at, the line integral is 0. Why is that? Because by this part of the theorem, the line integral from the end to the beginning is the final point minus the potential, I wrote phi, that should be F. The potential at the end point minus the potential at the beginning point. But the end and the beginning point are the same, so this subtracts to 0. Alright, so let's try actually evaluating some integrals now by the fundamental theorem of line integrals, also known in the text as the fundamental theorem of conservative vector fields, either name for it. If I want to take the line integral f dot dr for this vector field, 2xy, x squared are its components, how can I do that? Well, I check, df2 dx is 2x, df1 dy is 2y on the whole plane in an open, simply connected region. So this f is conservative. Now, I notice if this is the path, if I'm taking the line integral along this path, that's the unit circle, what could be the value of the line integral? Well, it ends where it begins. So it's the line integral of a conservative vector field around a piecewise smooth closed path is 0. This line integral is 0 without even doing a calculation. Except to see that it's conservative. Here's another one. Suppose f is this vector field, minus x over square root x squared plus y squared cubed minus y over square root x squared plus y squared cubed. If that looks familiar to you, you might recognize that as the force of gravity in the plane. If you have a planet going around the sun in the plane, this is its force field times a constant. The gravitational constant g times the mass of the one planet times the other, all times this gives you the force of gravity. So this is actually an important case. Gravity is a conservative force. It's a conservative vector field, the gravitational field is. So suppose we're moving in this field, which is just within a constant gravity, from the point 1, 0 to the point 0, 2 up here. So we go up 2 and over 1. And I wonder what the line integral is along that path. Well, turns out this is conservative, right? You can check it. And here's how you can check it. You can either take df2 dx equals df1 dy and check it, or you can just try and compute the potential directly and see if it works. So we'll just try and compute the potential to see if it's conservative. It has to be the partial integral of this with respect to x, since this is df dx, and it has to be partial integral of this with respect to y, since this is supposed to be df dy. So integral of this with respect to x, partial integral. Well, that looks hard. I'll substitute u equals x squared plus y squared. Treating y as a constant because it's a partial integral. Du is 2x dx, the derivative of y squared being 0. And so I make that substitution. I pull the minus out, and I multiply outside by a half and inside by 2. And now 2x dx is du, and square root x squared plus y squared is u to the 1/2. And so this is u to the 1/2 cubed du. And that one's an easy one to do. I'm just integrating u to the minus 3/2 and multiplying it by minus 1/2. Integral of u to the minus 3/2 is u to the minus 1/2 over minus 1/2. And these minus 1/2s cancel. The potential of this one evidently is 1 over the square root of u plus an arbitrary function of y that's the constant of integration here. And if I write square root of u as r, then this is 1 over r plus an arbitrary function of y. Now similarly, this has to be the derivative of f with respect to y. So if I take its partial integral with respect to y, by completely analogous steps, just integrating with respect to y, this thing is interchanging x and y. It's the same thing. You get 1 over r plus an arbitrary function of x. For these two to be equal, it must be that h of y and k of x are equal. Consequently, they're just a constant, right? This one depends only on x, this one depends only on y. So we observe that the most general potential is 1 over square root x squared plus y squared plus c. So let's choose c equals 0. That's a potential for this. Now, if we make that choice of potential, 1 over square root x squared plus y squared, then we know the line integral. We can put c down here, but I'll just say going from the beginning point, 1, 0 to the ending point, that should have said 0, 2. From 1, 0 to 0, 2 is f of 0, 2 minus f of 1, 0. Is 1 over square root 0 squared plus 2 squared minus 1 over square root 1 squared plus 0 squared is minus 1/2. So we actually did negative work. Remember, work is this line integral, f dot dr. We did negative work going from here to here. Well, again, in physics they put this backwards. F is minus the gradient of the potential, and work is minus integral f dot dx. So that they would say that if f is actually a force, then this would be a positive 1/2 work. I'm lifting it out to a larger distance. So it just depends on, in the book I think they say it's calculating the work against f instead of the work done by f. And so they justify them using a different minus that way a lot of times. Well, let's look at one more thing here. The analogy to calculus 1. This is the beautiful result. In calculus 1, you had the fundamental theorem of calculus that one of two parts was that if f is continuous on an interval, and capital F is any antiderivative on that interval, then the definite integral is just the antiderivative of b minus the antiderivative at a. This is how it was easiest to calculate these integrals, right? This is what made us able to evaluate all sorts of interesting areas. Similarly, the fundamental theorem of line integrals, if vector field f, this is in one dimension, right? F is a function of one variable x. If you have a function of more than one variable x, you have a vector field that's the gradient of some potential f, some function f, that's continuous in an open connected region containing a piecewise smooth curve C, then the line integral f dot dr corresponding to this is equal to f, the potential of the final endpoint minus the potential of the beginning point. So you just have to plug in the endpoint, plug in the beginning point, and take the difference just like you did in calculus 1. It's just now you use the potential instead of the antiderivative, and the letters are backwards. Here little f goes in the integrand, big F outside. Here big F goes in here, little f outside. But that's the analogy, and now this just becomes a special case of this, where you run a C along the x-axis and make this a function of just x.